Good afternoon. Today we will continue on the signal flow graph. So last lecture we stopped here. We already discussed a little bit. Let's just cap a little bit about the signal flow graph. Signal flow graphs is basically a representation, and instead of using the block diagram, we can use SFG or signal flow graphs. And this basically based on input nodes, output nodes, and the block can be replaced by an arrow, or it can be replaced by a branch with an arrow above this. So here is like some few examples that we discussed last lecture, which is basically identify the inputs R1, R2, and the output X1, X2. Then here, what we did is the relationship between them, we make it as, since here X1 equals plus R1, here is plus R1, then A2, X2, A12, X2, this is A12, X2, and A11, X1 as helpful. And also, we mentioned a little bit about something we call it input nodes, output nodes. Input nodes, which is the node that has everything going out, or everything going out from it. And output node, everything coming in, which is incoming branch. A path, which is a path or a continuous of branch, a continuous branch connected together. Then if they are passing from one side to the other side. Then we call also a forward path, which is a path from input node to output node. It can be done in several ways. There is one way, for example, using the straightforward, or another way by going in this path. So these are two paths as an example here. Then a feedback, or I would say like the loop path, we have here a couple of loops. The first loop here, this one, the second loop here. So these are two loops. Then when we look at loop X3, or this loop here, this loop, we can consider this as a self loop, because it starts from X1, X3, it goes back to the same loop, to the same node. Then the other thing we discussed, which is called the loop gains. So instead of saying when we travel from X1 to X2 to X3 to X4, we can multiply the gains by mentioning A21 times A22 times A43. Then this is called loop gains. Oh, I'm sorry, path gains. How about the loop gains? You can say for the loop gains A23 times A32. That's also a loop gain. The other thing that we mentioned, which is touching loops and non-touching loops. So when we look at it here, for example, this example, we have 4 loops, 2 orange loops, 1 green, and 1 pink loops. So when we look at it, we can say, or we can consider this, L1 and L2 are non-touching loops. L1 and L3 are non-touching. L1 and L4 are non-touching. While L2, L3, and L4, it's touching for all of them. Then when we look at the combination, we can say like this one. Is L1 touching? Yes. While L1, L2, L3, since L2 and L3 are touching loops, therefore you will neglect this part. And L1, L3, L4, L3 and L4 are non-touching, are touching loops, therefore erase it. L2, L3, L4, all of them are touching, therefore erase it. However, the L1, L2, L3, L4, all of them are touching, then we'll neglect it. So basically, when we deal with touching and non-touching loops, we'll deal with all of combinations. Start with 2 loops, all of the combination with 2 loops. Then with 3 loops, all of the combination of 3 loops, 4 loops, etc. Try to expand it more and step by step. We need to consider all of the possibilities regarding to the touching and non-touching loops. Now, here is the example. It looks scary, but it should be fine. Now, the first thing we need to determine the input node. Look at it. Where is the input node? X1. Why? So it's the only node that all of the branch going out. Therefore, definitely it is input node. How about output node? X8. Why? All of the branch getting in. How about X7? Can we consider this as inputs or outputs?
No, because there's input
and output. And any also a self loop, whatever. When you have a self loop, There is no way to make it an output node or input node, of course, yes. Now, number one, number two, done. Forward pass, which is how many path possible that goes from X1 to X8 without repeating the same node twice, which is the straight path, right? This is one path. So I would say, as he said, from X1, X2, X3, X4, X5, X6, X7. This is for forward path. Number one. How about the gains? Because here in parts number F, we need to find the gains. How about the path gains? 1 times A32 times A43 times A54 or 34. Is it 3 or 5? 5, 4. Yes. A65, A76. Then this is the first path gain. Okay, understood? Yes or no? Again, how did I find those? Basically, look at this one, this one, this one, this one, this one, this one. Multiply all of these gains. The next thing is to see, is there any other path? X1, X2, X4, then X5, X7, 6, 7, 8. So let me write path number 2, X1, X5, X6, X7, and to X8. X8. Then how about the gain for this? A42, A54, A65, A76. Okay, is there any other possible? X1, X2, X7. Okay, it looks good. Let's see. Change the color. X1, X1, X2, X7, okay, X8. So this is path number 3. Number 3 path, X1, X2, X7 to X8. So I would say the path gain number 3 will be what? A72. Is there anything else? No, that's it. Okay, how about, is there any other possibilities? Let me think about this. X1, X2. Let's see. I think there should be another one. But the thing which is, I don't know how to do it. Let's see. We have here, we mentioned 3 paths. 1, 2, 3. That's the thing. Yeah, I think there's 3. Yes. I think the loops, the trick in the loops, not in the paths. Okay. X1, X2, X7, X8. Okay. That's the 3 paths. So we are done now here with forward paths and with path gains. So we are done A, B, C, and G. Now, number D, feedback paths. Whenever we say feedback paths, we mean by this, which is, I would say, the loops, okay? No matter if it is self loop or whatever. Any loop, it's called feedback path. Let's go and try to figure out the loops here. Let's see how many loops can we have. Here is a loop, right? Here is another loop, right? Here's, yeah, loops, any loop, no matter what it is. All of the possibilities to have a loop. It's not a loop, right? Okay, but now these two are good, right? The next thing is to look at, there are two inner loops like here. Let's L1, L2, L3, L4. There is another loop here, another loop here, and a loop here. So I would say L5, L6, L7, right? Where? Please consider, tell me about the gain, not the gains, the X. Which one? X? X2 to X3? Yeah. We can do this. Like from X2 to X4, like this. That's correct. This is loop number 7. How about the same thing that we can do? Let me see. Can we do it in the other? In X5, can we go from X5 to X7 directly? No, we cannot. Let's see if there's anything, any other possibilities. X5 to X7. You cannot travel from X5 to X7. Yeah, because in A57 gain, it goes backward. Then how about going from X5 to X6, back to X5? We already have this loop. X4, where? X4 to X5. X4 to X5, no. X4 to X6. So far, we have 7 paths or 7 loops. Yes. 8. There should be 8 one. Which where is the 8? Number 8. Oh, yep. That's it. Yeah, I miscounted them. Yeah. X2. X2 to X7. X2 to X7. Then okay. Wow. Okay. This is loop number 9.
We can do the same path, closing the X6-5. For X to X7, it's 6-5 or 3.
You're right. Wow. Yes. The same path. Okay. So this is loop number 10. X5 to X7. X5, X7, X5 to X6 to X7. Then after that, backward to X6, X7. We already have 2 inner loops. Then there is no. We don't need to have an inner loops like this. I would say like it's loops inside it. So I would say we have 10 loops. Can we find the gains for them? Loop number 1. What's the gain? The blue. A77, right? Loop number 2. A5, 7, A65, A76. That's great. How about loop number 3? A76, A67. How about number 4? A65, A56. How about number 5? A54, A45. How about loop number 6? Say that again. Loop number 6, A43, A34. Loop number 7, A32, A23. Loop number 8, A42, fix it. A42, A34, A23. Let me see. Yeah, 23. That's good. How about number 9? A72, A57, A45, A34, A23. That's great. Then the last one, loop number 10, A72, A67, A66, A45, A34, A23. That's great. Thank you. So now we have 10 possibilities or 10 loops. When we look at them, is there any self loop? Loop? No. Loop number 1. That's great. That's the only self loop. How about in this? Is there any non-touching loops? Loop 1 and loop 3, loop 4, loop 5, loop 6, loop 7, all of them are non-touching, right? Loop 1, 3, 4, 5, 6, 7, all of them are non-touching to each other, right? I mean, there are many possibilities. I mean, we'll spend more than 1 hour to determine the touching and non-touching, but I would say, like just an observation, this one and this one, this one, this one, this one, all of them are non-touching to each other, right? Okay, let's see what do we need to find else, which is we already calculated the feedback, the loop gains, the self loops. So we're done. So here is just some demonstration determining the loops. So all the possibilities of the loops, they are already explained here in details. That's the loop number 10 that we think about. And the self loop, only this loop. We already explained this. Loop gains, we already written this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we already calculated all of these 10. So that's great. We did a great job. Path gains, we already calculated this. That's great. Now we are done with this example. The next thing is let's discuss the most important things in SFG, signal flow graph, which is a way of simplifying the block diagrams by converting the block diagram into signal flow graph or SFG. After that, we will simplify it to get the transfer function. So the overall idea is to find the transfer function instead of doing the combination of series and parallel blocks and move the pickoff points, etc., which takes a lot of time. So let's go to Mason rule. So Mason rule is basically the block diagram reduction technique that requires an application fundamentals of fundamental relationships in order to arrive to the system transfer function or to find the closed loop transfer function. Mason rule based on signal flow graph. So the first thing, convert transfer is this one again based on Samuel Jefferson Mason. He invented the signal flow graph and he invented the rule, Mason rule, and Mason rule is named because of his last name. His last name is Mason, then we call it Mason rule, and it was invented in 1953. This is very old science. Okay. So Mason rule, basically, we can say to find the transfer function between input and output, we already know where is the input, the output. We know where's the input node. We know the output node, right? To be as here is x1, x8. We need to reduce this to reach to get this. That's our target. Or basically x1 transfer function x2. That's the or x8. That's the idea to simplify all of this mess to be like this one. So how can I find it? Basically, C of S, which is the output node, divided by R of S, which is the input, output over the input equal the sum I equal 1 pi delta I divided by delta. Okay, what are those values? So the first thing, I starting from 1 to n. What's n? Number of paths. Do you remember in the previous example, we said the number of paths were 3, right? It was 3 number of paths. So here we would say like from 1 to 3. How about PI? What does PI mean? Means path gain. So do you remember how to find the path gain? We already did it in the previous example, just 5 minutes early. Okay? We know the path gains, right? The only things that remain, which is what's delta I, what is delta? No, let's see. Number of the forward pass, up path, determine the determinant of the system, delta, and delta I, determinant of the ith forward path. Say that again. The last example, there were 3 paths. So from I1 to 3. Which one the third forward path? Yeah, exactly. Yeah, the determinant of the ith. No, ith equal 1, 2, 3. So I would say, if, for example, we have 3 paths, it will be P1 delta 1 plus P2 delta 2 plus P3 delta 3 divided by deltas. How about P1, P2, P3? All of it, P1, P2, P3 is a path gain. How about deltas? Okay, it's kind of different. How to find deltas? Deltas, the first thing, let's calculate delta, then we will figure out how to calculate delta I. So delta alone, which is in the numerator, in the denominator, I would say, this one is called the characteristic equation. Okay, the characteristic equation delta can be found by looking at this. 1 minus sum of all individual loop gains plus sum of the product of the gains. All possible loops that does not touch, don't touch. 2 loops don't touch, minus sum of the gains of the loop, 3 loops don't touch, non-touching loops, and so on until we're reaching the higher order. While delta I, the loop that does not touch the path I, or any loop touch the path I, will be substituted as 0. Okay, what does this mean? Let's for some reason, like we have 3 loops, L1, L2, L3. So we will say delta, it's actually equal 1 minus L1 plus L2 plus L3, then minus, look at the possibilities of L1, L2 plus L1, L3 plus L2, L3, then plus L1, L2, L3. If we have 4, then we will continue. But the goal is C. You need to observe if L1 and L2 touching, if they are touching, remove it. Touching. If non-touching, keep it. Non-touching. If they are touching, remove it. Touching. Then L1, L3, if we assume L1 and L2 are touching, L2 and L3 are touching, therefore this one will be 0, touching. By going, for example, it will be much easier for you. I would say like touching will be 0s. Any touching loops will be eliminated. Therefore, this yields the overall will be 1 minus L1 plus L2 plus L3 minus L1, L3, and that's it. After removing all the touching. Oh, 1 minus plus. Yep. This is plus. This is minus. Therefore, this will be plus. Okay. Okay, between delta and delta I. Yep. Sum of 3 loops. Here were last 2 loops. 3 loops. The 4 loops and so on. Yeah, do you remember when I say about all of the possibility of the loops, like where? Yeah, let me see. Let me show it to you again. Like this, like this. For example, in this example, we said L1, L2, L3 are touching X. The only non-touching are what? L1, L2, L1, L3, L1, L4. So I would say here delta will be 1 minus L1 plus L2 plus L3 plus L4, then plus what? Look, L1, L2, plus L1, L3, plus L1, L4. Can we say minus the multiplication L1, L2, L3, L4? No, because they are touching. So we will say, we will stop here. That's delta. Okay, does this make sense? That's the thing, which is look all of the possibilities of touching and non-touching loops. When we go for an example, it will be much easier for you. I know sometimes it can be a little bit confusing, but when we do some examples, it will be much easier. Then the next thing, how about delta I? Delta I, first, after determining the delta, we will look at path number 1 and see if path number 1 touching any of the loops. If yes, then any loop that touching path number 1 will be considered as 0. So it will be another round of touching, non-touching, but look at any path touching the loops.
If it's touching, then delta I is 0.
Not delta, the loop itself. Let's assume, for example, delta. Let me go back to that example, the one that we already written here. Where is it? Here. Let's assume path 1 touch loop 1, loop 2. Let's assume this, but it doesn't touch loop 3, loop 1, loop 2, loop 3, but it doesn't touch loop 4. Let's assume for that. So we will say delta 1 will be 1 minus anything with loop 1 will be 0, loop 2 0, loop 3 0, loop 4 remains, so 1 minus L4. Then plus L1, L2, it's touching L1, L2, therefore they are zeros. L1, L3, since touching L1 and L3, they are zeros. L1, L4, L1 is 0, L4 times 0 will be 0, therefore this yields this delta 1. Okay? That's how we calculate delta. Then if we assume the other thing, delta 2, path 2 touches only L4. Therefore, we can say that the path or delta will be 1 minus L1 plus L2 plus L3. Anything L4 will be 0 minus or plus L1, L2 plus L1, L3, while L1, L4 will be 0 because L4 is 0. This is, I'm assuming this. L2, L3. I mean L2, L3, they are already touching, we're touching here. So we already neglected it. Okay. So I'll say just look at delta. So a second round of touching and non-touching. Look at delta itself, not the original situation. Again, when we look at an example, it will be much easier. But so far, any questions? Okay, let's go back here and see an example. So the procedure, the first thing, we need to calculate the number of paths, the path gains, number of the loops, the loop gains, consider non-touching loops for 2 loops, consider non-touching loops for 3, non-touching loops for 4, 5, etc. Then calculate delta I, then you are ready to go to find the transfer function. The good thing about it, you don't need to do parallel and series or move up pickup points for the transfer function or the block diagram. So we will avoid all of the rules that we applied before. So you can use it easy. Here's an example, then it will make the life much easier. So I think this example will make sense for us. The first thing, we need to calculate the transfer function C over R. Here is the signal flow graph after we converted the block diagram to signal flow graph. We realize this is how it looks like. Now, the first thing, let's identify the number of paths. How many paths do we have? R1. Move forward to C, right? So this is path number 1. So I would say path number 1 gain equals what? G1, G4, G2, right? Is there any other possibilities for a paths? What? Right? So we will say path 2 will be G1, G4, G3, okay? Is there another path? No more. Okay, that's it. How about the loops? How many loops do we have? we have this loop, right? And there is the big one. Is there any other loops? This loop 1, loop 2. Do you think there's any other loop? I think there is. This is loop 3. Okay. Do you think there's more? Or no, that's it? Think about it. This is making a fun of control system class, which is you need to think more. Think. Is there any other possibilities? I don't think so, right? So let's consider the loops. Loop gain, number 1 is what? G1, G4, H1. How about loop number 2? G1, G4, G2, H2. There's a negative, therefore don't forget to put the negative. How about loop number 3? G1, G4, G3, minus H2. Put a negative here. Okay? That's it. Now the next thing, since we have 2 paths, 3 loops, let's think about delta first, then delta I, okay? So delta itself, delta is what? 1 minus L1 plus L2 plus L3. Don't forget the brackets. Now, plus L1, L2. Are those touching or non-touching? Let's consider about this. L1, L2, L1, L3, L2, L3, L1, L2, L3. L1, L2, are those touching? Okay, erase it. L1, L3. Touching, right? L2, L3. Touching, right? L1, L2, L3. Touching, right? So we will stop here. That's it. That's delta. That's simple. Okay? The next thing is we can say C of S over R of S equals the sum Pi delta I divided by delta when I starts from 1 up to N, which is 2. We have 2 paths, right? So we can substitute it P1 delta 1 plus P2 delta 2 divided by delta. Okay? Now the next thing here, we already know delta. We know P1, P2. The next thing is to calculate delta 1 and delta 2. Correct? So how can I calculate delta 1 and delta 2? Delta 1 associated with path number 1. Now look at path number 1, which is the gray one. Do you think path 1, does path 1 touch L1, L2, L3? It's touching all of the loops, right? Therefore, we will say delta 1, substitute here, substitute L1 as 0, L2 as 0, L3 as 0. This yields what? Delta 1 equal 1. How about delta 2? Look at path number 2. Path number 2, which is the pink one. What do you think about this? Do you think this is touching all of the loops? Yes, right? Because look at the purple. It's touching loop 1, touching loop 3, and touching loop 2 as well. Therefore, all of them are zeros. This yields delta 2 to be what? 1. Then we can substitute it here. P1 delta 1 plus P2 delta 2 plus delta. You can substitute the variables. We already calculated it as, I would say P1 plus P2, because all of them times delta, divided by delta 1 minus L1, 1 minus L1 plus L2 plus L3. Okay? Now, I'm almost done. I mean, I'm done with Mason rule. The things that are remaining, which is the calculation. Substitute P1, P2, L1, L2, L3. Just substitute them. Where is it? We can substitute it here. The gains, I don't have enough space. Let's substitute it here. P1, it was what? Do you remember? G1, G4, G2 plus. How about P2? G1, G4, G3 divided by 1 minus. How about L1?
G1, G1, H1.
G1, H1. How about L2,
G1, G1,
G2, H2. Then minus L3, G1, G3, G4, H2. So you are done. Now this is a transfer function, closed loop transfer function. Okay? If we say, for example, assume G1 as 1, assume G2 as S, G3 as 1 over S, H1 as S squared, you know how to substitute them, right? It's just like do the calculation. So that's it. The goal or the overall idea is we go from this complicated one, where is it? To be a small one, to be like this transfer function. And here's the example is written, the answers are written in details, as we see here, touching loops. Then this is a closed loop. After we can do some simplifications. So because minus and minus will make this positive, positive. This will be negative. Don't forget, the minus will be distributed, right? Again, how will be distributed? Which is, there's a negative sign. We'll go here. We'll make this positive. These two terms will be positive because of the negative sign. And that's why we have these two terms positive. After that, if you want to simplify it more by taking G1, G4 as a factor, that's it. It's up to you. Or if you want to keep it like this, it should be fine. You're done. That's how we can find it. So you see, Mason rule is easy when you are using your brain. So, which is, my point of view, I mean, when you solve the Mason rule, you'll have a lot of fun. You'll enjoy solving the problems because you need to be clever. You need to be smart enough to identify the paths and the loops and the gains, which is something, in my point of view, is fun. Use this one. The first thing, identify the paths. I think it's already been shown in the graph. But anyway, the paths from R to Y. Again, how do I know R and Y? R, it's an input. Everything go out. Y is everything goes in. So how many paths do we have? We have two paths. The blue and the red path. So path number 1 gain is what? G1, G2, G3, G4. Yeah. How about path number 2? G5, G6, G7, and G8. That's great. Then the loops. How many loops do we have? One, 2, 3, 4. These are 4 loops. Can we use this? The one that I wrote. It is, my point of view, since it's crossing here, you cannot. No way. Because it has 2 completed loops in it. So if there is, then that's fine. You didn't need to go more. No, it wasn't like this. The previous examples, it was like this, something like that. Okay, so I would say we have 4 loops. What are these loop gains? Loop number 1 gain is what? G2, H2. How about loop number 2? 4. Leave loop number 3. H6. Loop number 4. G7, H7. How about delta? To calculate delta, let's consider about the possibilities of the loops. L1, L2, L1, L3, L1, L4, L1, L2, L3, L2, L4, L3, L4, then L1, L2, L3, then L1, L2, L4, L1, L2, L3, L4. Now let's think about this. Let's see, do we have 1, 2, 3, 4. Okay. They are considering L1, L3, L1, L4. Okay. L1, L2, are those touching? They are common in this node. They are considered as touching. L1, L3, they are far away from each other, right? So they are non-touching. L1, L4, non-touching. L2, L3, non-touching. L2, L4, non-touching, right? L3, L4, touching. L1 with L2 and L4, they are touching, right? L1, L2, and L3, touching. L1, L2, L3, L4, touching. So what remains? 4 non-touching groups. So we would say delta equal 1 minus L1 plus L2 plus L3 plus L4 plus L1, L3 plus L1, L4 plus L2, L3 plus L2, L4. Okay? Now, in order to find the transfer function, we can say transfer function C over R or Y over R here, which is P1 delta 1 plus P2 delta 2 divided by delta. Now, the things that we need to calculate, delta 1 and delta 2. How can I calculate delta 1 and delta 2? Look at path number 1. Path number 1, this path. What do you think this path touching what? L1, L2. Is it touching L3 and L4? No. Therefore, in order to calculate delta 1, consider anything related to L1 and L2 as 0. So 1 minus L3 plus L4. Then plus L1, L3, 0. L1, L4, 0. L2, L3, 0. L2, L4, 0. Nothing, right? So we'll keep it. How about delta 2? Delta 2, anything, path, the blue path, touching L3 and L4 will be 0, right? So it will be 1 minus L1 plus L2. Then do the plus. L1, L3, 0. L1, L4, 0. L2, L3, 0. L2, L4, 0. Therefore, nothing. Now, since I found everything, I'm ready to calculate the transfer function overall. Y over R will be P1 times delta 1, 1 minus L3 plus L4, or I would say I will put the minus in the book, minus L4, plus path 2, 1 minus L1 minus L2, divided by 1 minus L1 minus L2 minus L3 minus L4 plus L1 L3 plus L1 L4 plus L2 L3 plus L2 L4. Okay, after that, substitute the values. Substitute P1 with its own value with, where is it? G1, G2, G3, G4, P2, G5, G6, G7, G8, L1, G2, H2, L3, G3, H3, then L3, G6, H6, G7, H7. This will take a lot of time. Here it is, it's written in deep details. This is the overall transfer. Okay? In my point of view, the first thing that I prefer is to do it like the way that I did here. You see what I did here, okay? If it is too long, if you stop here, that's fine. If it's too long like this, but don't forget to find those If you miss those, it will not be counted, okay? If you find those and say, this is too long, you will substitute the values, the one that already calculated there, then it should be good for the exam, in terms of the exams. But in terms of the homeworks, the quizzes, the homeworks, you must write the complete answer, okay? If you're doing the homework, you must write the complete answer because you have enough time. But during the test, since you didn't have enough time, you did spend half an hour in writing these kind of expressions, then you didn't need to do that. Again, the exam in detail, or the answer of this example in details already been written. Here's example number 3. Okay, find the closed loop transfer function using Mason rule. Let's figure it out. How many paths? Let's see. Here, 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 here. Is there any other possibility for a paths? Are you sure? Yes. How about the path? What's the gain of the path? G1, G2, G3, G4, G5. Okay. How about the loops? How many loops do we have? First loop, second, third loop, right? The big one is number 4. That's it, right? We have 4 loops. Do you think there's any other possibilities of the loops? We have 4 loops. What do you think the loop gains will be? Loop 1, it is what? G2, H1. Loop 2, G4, H2. Loop 3, G7, H4. And loop 4, G2, G3, G4, G5, G6, G7, G8. No, there's no H. Let's think. Okay, 4 loops, 1 path. Now the next thing is to calculate delta. Delta equals 1 minus L1 plus L2 plus L3 plus L4 minus L1 and L2. Are those touching? Plus L1, L2 non-touching. L1, L3, L1, L3, L1, L4, yes, touching. L1 and L4 are touching. L2, L3, non-touching. L2, L4, touching. Okay. Now L1, L2, L3, non-touching. L1, L2, L4, touching. L1, L2, L3, L4, touching. So that this is delta. Now let's consider about delta 1. When you go for delta 1, path number 1 is touching what? L1, L2, L4, right? But it's not touching L3. So it will be 1 minus L3. That's it. Okay? Correct? Now the next thing is to calculate the transfer function, which is C of S over R of S, which will be P1 delta 1 divided by delta, which is P1 delta 1, which is 1 minus L3 divided by 1, the long term, minus L1 plus L2 plus L3 plus L4, then plus, I can write it here, plus L1, L2 plus L1, L3 plus L2, L3, all of it minus L1, L2, L3. Okay? Then you can substitute the gains that we have. Tamam? We have 4 loops, as I mentioned, touching L1, L2, L3. That's overall delta after substituting the variables, then this is this one. Okay. Do you remember this? Yeah. This is homework. Homework. I want you to enjoy it. Maybe you'll spend half an hour to solve it. Maybe half an hour. Maybe 1 hour. I'm not sure. But definitely you will not see it in the test. Okay, you will not see it in this because it's so long. So the thing which is 5 x8 over x1, the transfer function. Next week, x8 over x1. So it's due next Wednesday, which will be, I think, 29, right? 29 of July, right? 29 of July. Keep in mind, when you submit the homework, there must be a cover page. After that, write the homework. Must be nice, must be good, written good. I mean, if it is 100% correct, but if it's not nice written report, then you might get 7 out of 10 because of it. Okay? And you need to use also, use the paper from your notebook, use A4, okay? So far we have 2 homeworks. There's a homework that's submission. It will be Monday, right? Tuesday? Tuesday, okay. There's a Tuesday and there's a Wednesday, okay? So this homework number 2. Keep in mind, you must submit it in paper. This one. We used to do signal flow graphs, SFG or Mason rule, if and only if it was written in signal flow graph, right? Like the previous examples. It's already been written in SFG, then we can do the Mason rule. But here, it is written as a block diagram, not as SFG. And the question says, find the Mason rule, or using Mason rule to find the block diagram. You can solve this in different ways. One of the ways, by moving this summing point to here, they're doing the closed loop, right? The techniques that we used to do before. We know how to do this. This one way. Other way using Mason rule. Now in this example, let's use Mason rule. The first thing is to convert this block diagram into SFG. That's it. That's how it looks like. They are the same. You see, H1 with negative, right now, they are negative H1. H2 with negative, they are negative H2. Negative with H3, they are negative H3. You see it? Okay. Now, it's clear, or we know how to do this conversion, correct? Because this diagram will not be given to you. You will do it by yourself. So keep in mind to practice and how to do it. Basically, this is the input node, output node, inputs node. Then it starts with this here to E, and at E there is negative H2, negative H3, and so on. Make sure to understand how to do it, how to convert block diagram to SFG, and go to the last lecture because we already mentioned this last lecture, how to do the conversion. Now the next thing, since we already did this, let's figure out how to calculate the number of paths, loops, etc. How many paths do we have? There is one path, right? What's the path gain? G1, G2, G3, G4. How many loops do we have? 1, 2, 3 loops, right? So we have, what's the gains of the loops? Loop number 1, G3, G4 minus H1, so we'll put the negative here. How about loop number 2, which is what? G2, G3 minus H2, so put the negative here. How about loop number 3? G1, G2, G3, G4, H3 with the negative sign. Okay? All good? How about delta? Let's calculate delta. Delta, which is 1 minus L1 plus L2 plus L3, then minus L1 and L2 are those touching? L1 and L3. L1 and L3 touching, right? Touching. How about, we said L1, L2, L1, L3. How about L2 and L3? Are those touching? Yes, so there's nothing else. We'll keep it. L1, L2, L3, all of them are touching. Then we will stop here. How about for the path to calculate delta 1? Path number 1, touching loop 1, loop 2, loop 3, loop, all of these loops. So therefore, it will be only 1. As a result, we can say the transfer function C of S over R of S will be P1 delta 1 divided by delta. Then substitute them. P1 times delta 1, which is 1, divide over delta, which is 1, minus L1 minus L2 minus L3. Now, with this example, it's simple. So you can substitute them. Okay, this example, you must substitute them. You don't need to keep it here. So path 1, which is G1, G2, G3, G4 divided by 1 minus L1 minus minus will be positive plus G3, G4, H1. Then minus minus will make it positive plus G2, G3, H2. Then minus minus will make it positive plus G1, G2, G3, G4 times H3. And you can simplify it more, or I think you did it. That's it. Okay. Understood? Another homework. No, another homework. Come on, practice makes perfect. Practice makes perfect. So you have 2 problems for the homework. This is still for homework number 2. And this is due by Wednesday. I mean, if I can solve all of this, we can spend a lot of time on it, but I want you to practice. Okay, I'm forcing you to practice. When you are practice like this, and when you go to the test, it will be super easy for you because you're already an expert. You are an expert, and you can say, okay, my Mason rule is my game. So just do it. 29 is Tuesday. Okay, 30. I'm sorry. 30. Let me modify that. It is in July and July 30. Okay. That's it. Okay, here is an example. I think we are almost done, but let's see if there's anything else. Yeah, this is the last example. After that, we go to MATLAB. Find the response of the following control system such that D1 equal 1, A equal 1, K1 equal 1, K2 equal 2, KH equal 0.5, B equal -5, D1 equal 1/6. So when V is the step function of the constant value and U is the step function of a constant value. So the first thing, we have multiple inputs, 1 outputs, 2 inputs. The first thing, let's use Mason rule to solve for C over U. The second thing, C over V, okay? Or C over V, then C over U. So the first thing, assume U equals 0. The only thing that we have this. In order to do Mason rule, it's super easy. How many paths do we have? Only 1 path. How many loops? 1 loop. Therefore, once we figure out to use Mason rule, we realize that it will be the transfer function will be written 12 over S plus 3. I mean, so let's do it like this. L1 equal -G1 G2H. Path 1 will be G1 G2H. Delta equal 1 minus L, while delta 1 will be 1. Therefore, the output signal will be P times delta divided by delta, which is 1 times G1 G2H, over 1 plus G1 G2H. Substitute G1 G2 with its own value because we already have the values of G1 G2 here. Okay. Then it will be 12 over S squared plus 7S plus 12, which is 12 over S plus 3, S plus 4. You know this? Did you get it? Yeah, which is basically the first thing that we did, 12 over s squared plus 7s. Do you know how we find it? Substitute G1, G2, G3 with its own value, okay? So this example is very important for you, okay? So keep this in mind, mark it as a star, this example. Then after that, let's do partial fraction expansion, because here the transfer function equals C over V. Assume V as a step function 1 over S. This yields C as 12 over S, S plus 3, S plus 4. Then do partial fraction expansion, C1 over S, C2 over S plus 3, C3 over S plus 4. Then after that, after doing the partial fraction expansion, it will be like this. Then do it the time domain. Okay, so this is a cumulative example. We did Mason rule, we did the partial fraction expansion, we did a step response, and Laplace inverse. 4 examples in one. That's why I said mark it as a star example. The second thing, assume V is 0. Yes. Because we would like to find the step response. This is transfer function is C over V. Assume V as 1 over S, which is step response, step function, then it will be 1 over S. The second thing, assume V equals 0. Now we have U. The thing which is here, the paths, B times G2. The same delta, the same loops, but the difference, the only thing difference, which is the path. And do it the step response, 1 over S, partial fraction expansion. This yields C of t equal -5 plus 10 equal -3t minus 5 equal -14. Okay, understood? Here is the MATLAB command and how to use MATLAB in Mason rule. Okay, in Microsoft Teams, go to files, you will see MATLAB commands, or there's a folder called Mason rule on MATLAB. So there's an M file. Actually, the MATLAB don't have the built-in command to make the Mason rule. I mean, Mason rule does not exist in the MATLAB library. So what we have is there is somebody who did a program on Mason rule, and that's I already uploaded to you. Okay, so it's you can use that M file in solving this. It's not built in inside the MATLAB. It is a attached file, or it's been pre-programmed by somebody who put it in the internet. But the MATLAB, they didn't include it in their library. It's using somebody else. Then, how to do it? Here is an example. How to do it? I would say how to use the program. Pull the numerator, the denominator coefficients. Then there is an example on it. I'm not willing to explain to you. I would say that you can write it, okay, you can read it by yourself. And you can go to the MATLAB or to the folder that I already attached. You will see an example and the source file. Then this will be helpful, okay? This is not included in the homework, the MATLAB Mason rule, but I would say just it deserves to give it a try. So in case in the future, if you're solving for Mason rule, don't worry about it. You can go to the MATLAB, you can do the whole job. Or in your homeworks, if you want to validate your answers, you can do it using MATLAB. Okay, let me stop the recording.